Hi guys, in this opportunity we are going to resolve a problem related with the Hamilton equations. The problem says a particle of mass m moves in a central force field with potential Vr. The Lagrangian in terms of spherical polar coordinates r, theta, and phi is L equal 1/2 of the mass multiplying r dot squared plus r squared theta dot squared plus r squared sin square of theta phi dot squared minus the potential Vr. V as a function of r. So A, find the momentum PR, P theta, P phi. V, find the Hamiltonian H as a function of the coordinates and momentum. And C, write down the Hamilton's equation of motion. So in order to start solving this problem, what we do is we write the generalized momentum PR. So we are gonna resolve the part 8 of the problem. The generalized momentum PR P theta and P phi conjugated to the generalized coordinates, which are r, theta, and phi. So the generalized momentum conjugated to the generalized coordinates are by definition defined by these equations. PR is equal to partial derivative of the Lagrangian with respect r theta. P theta is equal to partial derivative of the Lagrangian with respect theta dot, and P phi is equal to the partial derivative of the Lagrangian with respect theta dot. Sorry, phi dot. So the Lagrangian as shown in the problem is L is equal 1/2 of the mass multiplying r dot square plus r square theta dot square plus r square sine square of theta phi dot square minus the potential V as a function of the position. So remember that these coordinates, they are spherical coordinates, okay? So we have this Lagrangian right here, right? Right here we have the Lagrangian of the problem. We know that we want to find the momentum PR P theta and P phi, right? We want to find those momentums. So the first momentum we are gonna find is PR, and remember that this is by definition dl dr dot, okay? So this is equal to, okay, we are gonna call this equation number 1, the Lagrangian number 1 equation. Okay, remember this derivative is respect with r dot, okay, with r dot. We are derivating the Lagrangian with respect r dot. But if you see this equation, the only term depending of r dot is this, the one I am pointing. So this term, the second term, and the third term, and the potential, they don't depend of the r dot. So the derivative with respect r dot of those terms are 0. So I can do something like this. I can write down 1/2 of the mass r dot squared, because I'm gonna write down the Lagrangian, plus r squared theta dot square plus r squared sine square of theta phi dot square minus the potential. Okay, but if you see, this term doesn't depend of r dot, so the derivative is 0, and this term doesn't depend of r dot, so the derivative of this term is 0 as well, and this one too, right? Sorry, I forgot to write down something here. I'm gonna write it real quick. So it's gonna be the derivative with respect r dot of 1/2 of the mass. Okay. Well, we get PR is equal to these two derivatives, and this one are 0. So we get dr with respect derivative of the Lagrangian with respect r dot of m divided by 2 of r dot square. Okay, so this term I'm gonna take it out from the derivative because it's constant. It's gonna be m divided by 2 derivative with respect r dot of r dot square. So by applying the power rule for derivative, we get m divided 2 multiplying 2 r dot. So the derivative of r dot square is 2 r dot. So PR is equal to, these 2 cancels with this, they cancel out, they cancel out each other, and the momentum with respect the coordinate r, in this case the position along the radius, is m r dot. And this is the first generalized momenta that we are looking for. Well, the next is gonna be, for example, the next momenta is gonna be p theta. Sorry, I wrote p phi, but it's p theta is equal to dl d theta. I won't write a long formula because it's gonna be kind of annoying writing a lot of formulas when we are solving this problem. But if you see what terms are depending of theta dot, you always you are gonna realize real quick what terms are gonna be 0 and what terms are gonna survive. So if we come back to the formula number 1, you will see that the term depending of r dot is gonna be 0, right? Because it doesn't depend of theta dot. The term with the phi dot is gonna be 0 because it doesn't depend of theta dot, and the same with the potential. So we are gonna have dl theta of 1/2 of the mass in this case it's gonna be the only term surviving is gonna be r squared theta dot square. Okay, the rest of the terms, they are the derivative of those terms with respect theta dot, they are 0 because they don't depend of theta. So that's the reason why I only wrote down this only term. That way I don't write a lot of terms solving this problem. But if you check it out, you will see that the only term surviving here is gonna be 1/2 of the mass r squared theta dot square, because that's the only term that is related with theta dot. So we get p theta is equal to, okay, 1/2 of the mass is constant. So 1/2 of the mass and r dot, they are constant because they are multiplying theta dot, but they are inside of the derivative. They are inside, so we are gonna take them out like this. 1/2, we are gonna write them out. 1/2 of the mass r squared derivative with respect theta dot of theta dot square. But applying the powers rule for derivative, we are gonna get this 1/2 of the mass r squared. The derivative with respect to theta dot of theta dot square is 2 theta dot. So we get 2 theta dot. If we see, this dot cancels with this these two. Sorry, these two cancel with these two as well, and the result is gonna be m r squared theta dot. So p theta is equal to m r squared theta dot. Okay, guys, let me write this down again. Okay, so I'm gonna call this equation PR number 2, and I'm gonna call this equation p theta number 3. And the next derivative is gonna be, I'm sorry, the next momentum is gonna be p phi. All right, p phi. So by definition, p phi is dl d phi dot. And the same, we write down this derivative with respect phi dot of 1/2 of the mass. This is the Lagrangian, okay? I ran in the Lagrangian, and remember, this is gonna be r squared sine square of theta phi dot square. Okay, why I didn't write down the other terms, the terms depending of r dot and theta dot and the potential? Because the derivative of those terms with respect phi dot are 0. So there is no, it's pointless writing all those terms, because we are going to be writing terms that they are going to be 0. So because they don't depend of theta dot, of phi dot, they are 0 as well. And we do the same as we did before in the last calculation. We write p phi. Okay, the terms that are multiplying phi dot, we can take those terms out of the derivative. So we get 1/2 of the mass r squared sine square of theta derivative with respect phi dot of phi dot square. And you know that this is gonna be the derivative of phi dot is gonna be 2 phi dot. You know, the derivative with respect phi dot of phi dot square is gonna be 2 phi dot. So we write down 1/2 of the mass, r squared, sine square of theta. Okay, 2 phi dot, and this 2 cancels with this 2 out. Their final result is gonna be p phi equal to m r squared sine square of theta phi dot. Okay. So this is number 4. This is number 4. This is number 4. Okay. Okay, we have the first question solved, the first part of the problem, part 8. Find the momenta PR, p theta, and p phi. So PR is the number 2 equation. We have the calculation, the result here. Actually, I'm gonna highlight it. The same with p phi, and the same with p theta, and the same with p phi. All right. So now the next step is solving the second part of the problem.